We turn on the tap every single day and probably don't give it a second thought. But have you ever stopped to wonder about the incredible hidden journey that water takes before it's actually clean and safe enough to drink? Well, that's exactly what we're going to pull back the curtain on.
Right? It seems like such a simple question. But the answer? Well, it's this fascinating story of nature, science, and some really brilliant engineering. It's not magic, not by a long shot. It's a carefully designed system that's literally protecting our health every single day. All right, so here's our game plan. We're going to start with what's actually hiding in the water to begin with. Then we'll check out nature's own cleaning crew, and finally we'll dive deep into the engineering that makes it all happen. Okay, so first things first, a simple fact. Water out there in nature is almost never pure. As it's flowing in rivers or seeping through the ground, it's picking up a whole cocktail of different materials, and all of it needs to be dealt with.
So these impurities really come in three main flavors. First, you've got suspended material, little particles just floating around. Then there's dissolved material, which is chemically mixed right into the water itself. And then you have the really tricky ones, colloids. These are microscopic particles that are so incredibly tiny, they just refuse to settle out on their own.
So, to get a handle on all this, engineers sort these contaminants into three big buckets. You've got physical stuff, like things that make the water cloudy, then chemical, which includes things like minerals and metals, and finally, the big one, biological. We're talking about the pathogens that can make us seriously sick. Let's zoom in on one of those key physical things, turbidity. Now, this isn't about how much stuff is in the water. It's about how cloudy that stuff makes the water. Here's a great way to think about it. Imagine you drop one little pebble into a glass of water. Almost no turbidity, right? The water's still clear. But what if you crush that exact same pebble into a fine powder and stir it in? Suddenly, the water is super cloudy, highly turbid, even though the actual amount of rock in there hasn't changed at all.
Long before we had treatment plants, the planet had its own ways of cleaning water. And these natural systems are so effective, they've actually inspired a lot of the engineering solutions that we rely on today. I mean, the Earth is incredible at this. Rivers, lakes, even the soil itself, they're fantastic natural filters. But, and this is a big but, these systems have their limits. They can get completely overwhelmed by the heavy pollution that comes from human activity. And that's where engineering really has to step in.
So what's the secret sauce for nature's cleanup crew? It all comes down to metabolism. You've got these tiny microorganisms in the water that are essentially eating the pollutants. They break down all that complex waste to get energy and to grow, acting like the planet's very own microscopic water treatment plants. It's pretty amazing. This is where the engineers come in. They looked at what nature was doing and basically asked, okay, that's brilliant. How do we make this faster, more reliable, and put it under our control? The answer to that question led to, well, modern water treatment. And that question led to an absolute explosion of progress. This quote really says it all. For literally thousands of years, how we cleaned water barely changed. But just in the last 100 years or so, our understanding has just skyrocketed, leading to these massive, incredible systems we have today. So let's break that down. What's the real difference here? Well, nature's process is pretty slow, and it really depends on the local conditions. Engineered systems, on the other hand, are built for speed and absolute control inside a dedicated plant. They have one very focused goal: producing safe, drinkable water for all of us, day in and day out. Okay, now we get to the really cool part, the great separation. At its heart, that's the main job of a water treatment plant, separating all those unwanted things out of the water. And it happens in a series of really smart, carefully designed steps. And it all kicks off with something surprisingly simple. We just let gravity do the heavy lifting. The water is moved into these huge, calm tanks, and we just wait. The heavier stuff, the sand, the silt, the grit, it all slowly settles down to the bottom. And don't underestimate this simple step. Just look at this number. A well-designed settling tank can get rid of more than half of all the suspended stuff right at the beginning. That makes every single step that comes after it way more efficient. But what about all the stuff that's left over? Remember those colloids we mentioned? They're way too small and light. Gravity just doesn't affect them. They will happily stay floating in that water pretty much forever, unless we do something about it. So what's their secret? Why don't they just sink? Well, it all comes down to physics. Each of these tiny particles has a negative electrical charge. So think of them like tiny little magnets, all with their negative poles facing out. What happens? They constantly push each other away. That repulsive force is just strong enough to beat gravity and keep them from ever clumping together.
So, if they're like tiny magnets pushing each other apart, how on earth do you get them to clump together? Well, you fight chemistry with chemistry. It's a process called coagulation. We add a chemical that has a positive charge. That positive charge cancels out the negative charge on the colloids, basically turning off their little force fields.
It's a really neat two-part process. First, we rapidly mix in that coagulant chemical to make sure it gets to all the particles. Then, once their charges are neutralized, we switch to a very slow, gentle mix. This is called flocculation. It encourages the particles to just kind of bump into each other and stick together, forming these bigger, heavier clumps called flock. And now, that flock is finally heavy enough for gravity to do its job and it settles right to the bottom. All right, so most of the gunk is gone, but we're not done yet. Think of this next step, filtration, as the final polish. The water is passed through these big beds of sand and other grainy materials. This step catches any last little bits that might have escaped, making the water absolutely crystal clear.
Okay, the water looks great now. It's crystal clear. But the biggest dangers are the ones you can't even see. The final steps are all about tackling those invisible threats, the biological contaminants.
And that brings us to the final and maybe the most critical safeguard of all, disinfection. A disinfectant, usually chlorine, gets added to the water. Its only job is to kill or neutralize any harmful pathogens, bacteria, viruses that might still be hanging around. This is the step that has saved countless lives from waterborne diseases like cholera and typhoid. It's a huge deal. So what's next? Well, we're starting to think about water in a more circular way. This idea of indirect reuse is getting really important. It's where highly treated wastewater is put back into the environment, say into an aquifer. That natural system acts as a final buffer, letting nature do one last polish before that water is eventually drawn out and treated all over again to become drinking water.
So, from a muddy river to your kitchen sink, it's an incredible journey, isn't it? A mix of physics, clever chemistry, and just brilliant engineering. But the story isn't over, and it leaves us with a pretty big question. As our world keeps changing and new pollutants like microplastics and pharmaceuticals show up, how will this vital process need to evolve to keep our water safe for generations to come?